Hello again, fellow video freaks and AV geeks. It's Dr. Yo with another episode of Video Synth Tools and Techniques, where I share what I've learned about video synthesizers and the LZX modular ecosystem. This is a special episode because I get to share what I've learned about DSG3, the dual shape generator from LZX Industries. And it's one of my favorite modules because it's so versatile. It allows us to modify our images in many different ways and also combine and blend images in unique ways. Now, when I first heard the term dual shape generator, I took that literally and thought that its primary purpose was just to create patterns for direct video synthesis. And that is one of its functions, but that is not the end of its capabilities by any stretch of the imagination. And it wasn't until I saw some sample videos posted by our fearless leader, Lars Larson, that I realized that DSG3 is the successor to the Expedition series module Arch, which is a nonlinear function processor. DSG3 is like two arches, plus ramp generators built in. That is what makes it a shape generator. It's not quite the same, doesn't have all the functions of Arch, but one thing it does have going for it is user friendliness. Like all the Gen 3 modules, the switches are designed for long-lasting use. And those switches make it really easy for you to test out all the different options on DSG3. DSG3 is divided into two identical submodules called shapes. Each shape has two channels. Each channel has 5 image processing functions: negative, single fold, double fold, logarithmic, and exponential curves. Then those two channels are combined into a blending engine, which gives us 4 different outputs. We can find the sum of those two channels, the minimum brightness or value. In Photoshop blend mode terminology, that would be the darker color. You can find the maximum or lighter color, and you can find the absolute value, which corresponds to the Photoshop blend mode of difference. It's the absolute value of the difference. And we'll be exploring that in quite a lot of detail in the demonstration. All right, let's have some fun with DSG3. Starting from the ultra basics, if nothing is plugged into the DSG3, then it acts as a ramp and pattern generator, living up to its name as a shape generator. Let's take a look. I've got my encoder ready to go. I'll take the absolute value output of DSG3, plug it into my encoder. And what we're seeing here is a blending between the two ramps. We have the horizontal and vertical channels here, and with nothing plugged into the inputs, the ramps are normal to in. So we could look at this, from different outputs. That's the sum. We've got the minimum and the maximum, and back to the absolute value of the difference. But if we really wanted to analyze what these functions do, we would want to just isolate a single ramp instead of seeing the blending between two ramps. And because the best way to visualize that is on the waveform monitor, we want to actually use a horizontal ramp, because that's going to correspond directly to what we see on that waveform monitor. That means I want to break the normal to the vertical input. If I put a dummy plug or a 0 voltage source into that vertical input, we're breaking the normal to the ramp, but we're not supplying any other signal. And so we're basically just getting black on that vertical channel. So now what we're seeing is the absolute value of the difference between the horizontal ramp and black. And predictably, horizontal ramp minus black equals horizontal ramp. We're subtracting nothing here. If we flip the switch on this vertical channel, then we will actually be supplying white to that channel. Now what we have is white minus the horizontal ramp, basically inverting the horizontal ramp. Just doing it a different way mathematically than if we actually directly inverted the horizontal ramp. We get the same result. Then we have the folder or rectifier. In the middle position, we are not folding. In the up position, we're folding once. Now take note of this. We see that our level goes all the way up to white. So with a normal rectifier, what you would get, if you supply a sawtooth or a ramp, one of these, then it's going to set a threshold right in the middle, and it's going to invert everything above that 50%. Normally, this would be with a bipolar signal, but for this unipolar signal, the zero line is actually at the 50 IRE mark. If this was just a rectifier, then what we would see when we flip the switch up is a triangle wave that only went up to 50%. But the circuitry here is designed to compensate for that. It actually amplified the signal so that it's at full range. And likewise, if we put this into the double fold setting by flipping the switch down, we see we're getting 2 cycles of that triangle wave. And it's once again going all the way up to white. Then we come to the exponential and logarithmic switch. In the up position, we've got a logarithmic setting. And in the down position, it's an exponential setting. And you'll notice that the ramp actually looks more linear in that exponential setting than it does bypassed. That is a true linear ramp. And that is a linear ramp that has an exponential curve applied to it. And that actually kind of looks more linear to our eyes. And that's just the way human vision works. Our eyes have a logarithmic response curve built in. When we look at a linear ramp, it looks wrong. But when we apply an exponential curve, it cancels out the logarithmic response of our eyes, and it looks linear even though it's really not. All right, cool. So we can, of course, combine all these things and get different looks and different patterns, and it's all pretty cool stuff. But what I'd like to do is show you a different pattern, because I think that's going to give us a better sense. If we just look at the combination of these 2 ramps and flip all switches, see what they do, we do get some patterns. And those are kind of interesting, but they're of course constrained to the aspect ratio. So we're not going to get actual circles anytime. We're always going to get these ovals. That's because the aspect ratio of video is not square. And these ramps are constrained to the video frame. So I'm going to set up a patch here and come back to you with a better image that's going to give us a better sense of how these blend modes work. To give an intuitive sense of how the blend modes on DSG3 operate, I want to use several different types of images. Starting with a 1-bit image, something that just has pure black and pure white. I've got that all set up so I can just show you what each one looks like. So here I've got a pattern of black and white bars going from left to right. And we've got another pattern that's going from top to bottom. And those are already patched into DSG3. Let's see what the various outputs look like. Here's the sum. We're seeing 50% of the first image added to 50% of the second image. Wherever both of them are white, we get white. Wherever both of them are black, we get black. When one of them is black and one of them is white, we get 50% gray. Okay, so that's a weighted sum. Let's look at the minimum. All right, so we're getting predominantly black here. Anytime there's black anywhere in the image, the final output will be black. Anywhere that's white on the image has to be white on both channels in order to output white. And then we've got our maximum. Anywhere there's white on either of the channels, we will get white on the output. And in order to get black on the output, it has to be black on both channels. Then finally, we have the absolute value of the difference, and we get a checker pattern. We're subtracting one from the other. Cool. So that's how it works with just a 1-bit image. And because it's a 1-bit image, if we flip these switches, we're actually not going to get very much of a result. It's not very artistic, right? So we don't really want to do that with this. We need some gradient in order to see the effects of the folding and the exponential and logarithmic settings. And I've got some test images prepared that use radial and circular ramps. I think that'll give us a better sense than the standard ramps that are built into DSG3. Okay, here are the test images I prepared. First, we've got this radially symmetrical figure, and then we've also got a circular ramp. And I've patched those into DSG3. Let's see what the various outputs look like there. Here's the sum, and all the switches are in their neutral position. We can start playing around with them and see what they do. Making those negative isn't really that interesting, but if we start working with the folders, things start to get more aesthetic. There's 2 folds on that circular ramp. That's pretty cool. And then we've got our radial symmetry. There I've doubled the frequency of that radial pattern by putting the fold into the up position. And we can go for the down position, and we've quadrupled that frequency. And we can, of course, combine these and get all kinds of cool effects. We haven't even begun, really. So if we flip all switches and see what they do, we'll get some cool results. It's kind of rosette patterns. And again, this is with the sum output. Let's see what the other outputs look like. Got the minimum. And predictably, that's going to be predominantly black and dark, because we're always going to see the darker of the 2 inputs. Cool. Got some sort of, I don't know, Batman logo kind of images there. Very cool. So that's the minimum. And then we got the maximum. And predictably, that's going to be predominantly white. Same principles apply. You can get all kinds of cool effects here, especially with the folder. And then we can change the curve using these logarithmic and exponential switches. Could do this all day long. That is pretty awesome stuff, my friends. Love that. And also, if we make one of these negative, we will see that we're getting a white background instead of a black background, right? Because we're always going to see the maximum of the 2 channels. So anywhere it's white, it's going to be white in the output. And then finally, we come to the crown jewel here, the absolute value of the difference. And here's where we kind of go into another whole dimension of possibilities. With all these switches in their various positions, we can get a pretty wide variety of patterns. So I think this is a really good example in terms of showing us all the different sort of possibilities that we can achieve with various settings. If we start looking at naturalistic images, such as photographs, we can start to see the real creative potential for processing external video. I've got a couple photos here prepared so you can see. There's some trillium flowers at Forest Park in Portland. And then we've got the Columbia River Gorge. Pretty cool stuff. All right, so those are patched into DSG3. And if we take the sum, we're getting a 50-50 blend. Neither one of those images is going to be at full strength. The maximum of either image is going to be 50%. But where 2 images overlap, we could potentially get a value up to 100 IRE. And we've got the minimum. And predictably, we're getting a kind of a dark image, because anywhere one image is brighter than the other, we will see the darker of those 2. And of course, we got the maximum. And in this case, I think this is the most artistic, because we're seeing those flowers really kind of shining through. We're getting this cool superimposition. And of course, this is all going to be dependent upon the imagery you use. But we can see the creative potential here of using that maximum output to sort of extract the brightness from an image and superimpose it over another. And then we've got the absolute value. This is giving us kind of a busy and chaotic image because of the content of those images. But if we pre-process the images before they hit DSG3, then we'll have quite a bit more creative control. I've already got that set up here with a proc module, and I'm using these tip-top audio stack cables because I do want the ability to amplify these images so that we can make them brighter. And the trick to that is to send the same signal into both the A and B inputs of proc, and that way we can actually add it to itself. Okay, so I've got my TBC2, that's one of the images, and I've got the VO3B supplying the other image, and then those are going to go, of course, into DSG3. And I've got a neutral setting here on my proc knobs, so we're getting pretty much the same thing we did before. The reason we're getting a neutral image is because the B input knob is set to 0. We're only getting the A input flowing through, and we're not applying any bias. Okay, let's see what happens if we reduce the intensity of one of the images by lowering this value. So we're basically not adding that image into the mix. And we do get a little bit of a ghost of it there. And that's just because proc is not really a perfect subtractor here. It's not actually putting out a 0 voltage here. But you see the principle. We're able to reduce the influence of that image. Okay, so cool beans. Likewise, with the other image, reduce its influence. Then we come to the bias controls, and those are giving us really a lot of creative control. And the reason that this is working so well is that DSG3 will accept a bipolar signal. We can apply a bipolar signal here. We can apply a value that is below 0, and the math will still work. It's always going to output a signal from 0 to 1. It's unipolar. But inside the brain of DSG3, a negative voltage is perfectly allowed. If we reduce the bias here, we're sending a negative value into that horizontal channel. And if we bias up, we're sending more and more of a positive value up to the point where we're actually going to clip. All right, so that's kind of an interesting fact, an interesting trick of DSG3, that we can send an inverted signal that is actually below 0, as we do here. And that'll work just fine. And that'll give us some artistic control that we wouldn't have otherwise. Good to know. So as I play with this, I can increase the amplitude. I can actually amplify that up to 2 times value because of my clever patch here. And then I can reduce the bias. And in this situation, we're sending out a very hot signal that's been biased down so that we're getting actually a range from -1 to +1. You can do that on the other side too. Set that the same way. And we're getting a really wild result. And really, just to bring this point home, let's look at just one of these signals so you can see how this bipolar input is going to operate. All right, so I'll set everything back to neutral. Okay, so there's my image with no transform applied to it. We're not biasing it up and down. We're not amplifying it. We're not attenuating it. Okay, so I can amplify it. I can attenuate it. All good stuff. And now let's try biasing it. So if I bias it down, it's actually going to go into the negative voltage. And look what happens. If I go all the way down, we're getting a negative image just by biasing. So what's happening inside DSG3 is it's finding the difference between this image and nothing, giving us a negative image. All right. But then if we start playing with the bias here as well, we can actually get the solarization effect that we did before using the folder switches. So, wow, that's cool. So now I'm supplying an image that goes from -1 to +1, and DSG3 is actually folding that, even though I'm not using the folder. Very cool. So this is something that we can do with pre-processing, and then we can actually even layer folds on top of that. That's an absolute value of a bipolar signal that's been folded once or twice. And we may need to adjust the amplitude here and play around with these, because the rectifier, the folder inside DSG3 is kind of internally amplifying things, and we're ending up with a really hot signal. But you can see that there's a lot of potential here if we pre-process the image before it hits DSG3. This time I'm using proc, but another module that comes in really handy for this sort of pre-processing is the VU005 wave shaper. So that's from Synth, one of my favorite modules, and I did a whole video just about that. We could take that instead of the proc as our input to DSG3 and see what kind of result we'll get. So I want to go to the output, not the B input. Okay, so there it is with no transforms applied. If I play around with the level and the shape of the VU005, also known as the gain and the offset, we'll get different looks. Okay, but that's not really that interesting right now. But if we start to apply folding to that, then we can get a wide variety of different looks that we couldn't achieve any other way, because VU005 is actually changing the contrast curve before it hits DSG3. Cool. And likewise, I could do the same with my other image, plug that in, see what kind of craziness we can do by taking the absolute value of those two pre-processed images and play around with both of their shapes, and of course play around with the different fold settings. And again, as I mentioned in my VU005 video, these logarithmic and exponential switches do something similar to what you can get with VU005, but it's not really the same thing. All right, crazy. So we've made it even more busy than it was before, kind of against what I was saying earlier, but it's super fun anyway. Now we can't actually animate this. In other words, there's no control voltage input to VU005, but we could probably put this through a VCA and get something that was kind of nice. All right. So there's some more creative madness with DSG3. And yeah, what happens if we supply moving video? Oh my goodness, now things are really getting crazy. All right, let's watch TV. Let's see what's on. If you've got more than one video source going into your synthesizer, you can do some really crazy and really creative stuff. I can watch TV like this all day long and all night long. This is the way to watch television. Taking it and mutating it, turning it into something else, making it our own. Now we come to the magic, the killer app of DSG3, color cycling, or in this case, luminance cycling. I'm only cycling the brightness of this image. The ingredients that you will need to achieve this effect are some kind of video image. It could be a natural one like this or a synthesized pattern. You'll also need a low-frequency sawtooth wave. You'll need an absolute value processor and a folder or frequency doubler or rectifier. Those are the ingredients. The basic path is you're going to combine your video image with a low-frequency sawtooth, find its absolute value, and then pipe that through a rectifier. You may also need to use a processing module. You see I've got a proc here in the mix, and that's necessary because to get a clean cycle, the amplitude of that low frequency oscillator is extremely critical. You may need to spend quite a lot of time actually tweaking the amplitude of that LFO in order to get a clean cycle. All right, now that you understand the basic principles, I'm going to tear this patch apart and I want to build it up from nothing and sort of illustrate the concepts as we go. Okay, so I'm going to take all of this stuff out. This is my LFO. And here is the patch going from one side of DSG3 to the other. What I'm going to do to start with is I'm going to take the absolute value of my video image against a static voltage. Okay, I've got my proc connected here. And with nothing going into proc, the bias acts as a static voltage generator. Currently, I've got a 0-volt output. Nothing's plugged into proc, and the bias is set to 0. At this point, as we saw before, I am subtracting nothing from the video image. All right, so if I increase my bias knob on proc, I'm sending a brighter and brighter image into the vertical channel of DSG3. If I go all the way up to 1 volt, I get a negative image. I am subtracting white from my image. Or we could also think of it as we're subtracting our image from white. It works out to be the same. All right, so if we applied a sawtooth to this, what we would get is a transition from a positive image to a negative image, and then an instantaneous jump back to that positive image. But that's obviously not a cycle. How can we achieve a cycle? Well, think this through. What we want is the image to actually fold downward back into the positive zone. In other words, we've got a positive image with a 0 voltage. We also need to see a positive image at 1 volts. We want to see, okay, at 0 volts positive, 0.5 volts negative, and 1 volt positive again. If we think that through, then the obvious solution will be to run the signal through a rectifier. What that's going to do is when our video image reaches a value of 0.5 volts, then any value above that is going to get folded downward. And we will get that symmetrical triangle wave that we saw before, except that triangle wave is going to be applied to the video image rather than just a simple waveform. Okay, so our patch is going to be, we're going to take the absolute value of one side of DSG3, that's shape 1. That's going to go into one of the channels of shape 2. I'm going to put a dummy plug into, in this case, the vertical input of shape 2, breaking the normal. We're only going to be using this side of DSG3 as a rectifier. And we're going to take the absolute value. And now what we see is a solarized image. And that's to be expected because I am applying a single fold. When we apply no folds, we get whatever is coming out of the absolute value of the first shape. And right now I've got a negative image. I can put that back to positive by bringing my static voltage to 0. Okay, and then once again apply a single fold and we get that solarization effect. All right, now let's see what happens if we adjust this static voltage through the entire patch, through the absolute value, through the rectifier. With a static voltage of 0, we get this solarization effect in which we can see that the clouds in the sky are white. Okay, let's set this to 0.5 volts. Now the clouds in the sky are black and window rock here is white. Okay, then bring this up to 1 volt and we're back where we were when we started at 0 volts. We've got a true cycle here. The clouds are white, the rock is black. All right, and if we were able to automate this and make this go from 0 to 1, boom, we get right back where we started. We have a cycle. Okay, so that's the purpose of applying the sawtooth here. We're going to go from 0 to 1, end up right back where we were, and then snap back to 0 precisely. Okay, we're not ping-ponging back and forth. We're going to be doing a ramp up. So from 0 to 1, and then immediately back to 0. Cool. All right, so that is how this works. Let me just patch that in. I've got my DWO3 here, and it's currently got a sawtooth output. I'm actually sending it through a sample hold patch in order to quantize the voltage to whole frame intervals, as I described in a previous video. But you could just patch the sawtooth directly in. It might be fine, it might not, and it's going to vary depending upon a million zillion factors. It could just be, the temperature in your room that day. There's no way of knowing. But in my case, I always run my control voltages through a sample hold circuit. That's kind of optional in this case. And so that's my sawtooth. It's going to go into my proc. And that proc output is feeding the vertical channel of shape 1, which is being compared with the video image to get the absolute value. Let's see what that looks like. Beautiful. We've got that cycling. It's operating just as if we were turning that proc static voltage knob from 0 to 1 and snapping back to 0, 0 to 1, 0 to 1, 0 to 1 over and over again. Now we come to our proc amplitude. Today, with this particular oscillator, I only need to attenuate that signal just very slightly in order to get a pretty clean look to my cycle. If that was off by just a little bit, then we would not get a perfect cycle. We're not going to go all the way from 0 to 1. So this is kind of tricky. This can be a pain to tweak on this. Sometimes it takes a really long time to find exactly the right value for that amplitude adjustment. You might need to amplify it. You might need to attenuate it. Again, today I just needed to attenuate it a very small amount. I'm going to show you a trick that'll make it easier, and that is simply to use the internal ramp of DSG3 and the waveform monitor. It'll make it a lot easier to dial in the exact value. I'll unplug the video image from the horizontal input to shape 1 of DSG3. And now we are finding the absolute value of the internal horizontal ramp compared to the incoming sawtooth. And that gives us the illusion of motion from left to right. Cool. So if we look at our waveform monitor and the video image, what we want to see is no jumping. And there is just a little bit of a tiny jump there where the waveform is snapping a little bit to the right. Well, that spatial position of the wave is directly correlated to this knob. The amplitude of the incoming sawtooth is going to precisely determine where that cycle happens. If we have not enough amplitude, our voltage is not high enough, then the wave doesn't move enough in order to hit the cycle point. If it had too much amplitude, then that wave would move too much, and we would get kind of a jumping backwards. Okay, so that's the basic principle here. And you want to dial this in until that cycle is perfect and it doesn't jump forward or back. It may never be exactly perfect, having to do with the exact precision of the rectifier. It may not be perfectly symmetrical. Your incoming sawtooth may not be perfectly shaped or formed. And like I said, there's a million factors that work into this. You may find that changing the frequency of the sawtooth makes it easier. So I've got that going on here. Let me show you. Here's my sawtooth wave, and I can increase that frequency, and that may make it easier for me to find the exact cycle point because I don't have to wait as long, and the kind of duty cycle of this tweak process is faster. I'm iterating faster on finding my way through this phase space. All right, that looks pretty good. and I can reduce the LFO frequency, and it's not perfect, but it's good. Now I'll just plug my video image back in, and I've got my cycling. Pretty awesome. Now we can play around with the switches here on DWO3. If we invert either one of the video image or the sawtooth, then we're going to reverse the direction of the movement on screen. Right now, neither one of these switches are in the negative position, and what we're getting is the image in the sky is kind of moving from top to bottom. If we inverted either one of these, we would reverse that direction, and now the colors are moving from bottom to top. We can also fold the video image. We can apply a folding before it even gets to the absolute value comparison. And that's giving us a more Baroque image. We could do 2 folds, and that's looking pretty busy, but you know what? It might be the effect you're going for. It looks pretty cool in the sky there, actually. And of course, we can apply the logarithmic and exponential curves to change the look of the image. I do have my VO5 in here too, and I've adjusted its level and shape in order to get the contrast and the detail that I want. But I can also layer these logarithmic and exponential curves on top of that if I want. And we come to the sawtooth itself. And as I said, if we invert that sawtooth, we'll reverse the direction. If we apply a fold to the sawtooth, we'll get a ping pong effect, as if we had applied a triangle wave instead of a sawtooth. And this isn't really the best way to achieve that. If you wanted that ping pong effect, then really just use a triangle wave instead of a sawtooth. And there it is with 2 folds, and we're getting a double ping pong effect. And notice that as I increase the folding, we're also increasing the speed. The temporal frequency is also doubling or quadrupling. All right, I'll put that back to no folds on that sawtooth. If we apply a logarithmic or exponential curve to the sawtooth, we're going to change the speed over time, and it's going to speed up or slow down, giving us an ease in or ease out effect. Let me try the other position to see what that looks like. If you do use the logarithmic or exponential setting, then you'll probably need to change the amplitude of your incoming waveform to compensate, because simply flipping those switches is going to require a recalibration of the whole system. In this case, I just want a simple linear cycling with no frills and no speeding up or slowing down. And once again, I may need to adjust that value even within the same session. From moment to moment, from second to second, it may change because we're in the analog domain. But if we have this going faster, that becomes less and less of an issue. If we increase the frequency of that sawtooth, that's going to mask any of the discontinuities that may come about from this patch and all the sophisticated electronics involved. Now, as with anything, if you wanted to do this in color, you would need more modules. If we wanted to do an RGB version of this, then we would need 3 DSG3s or 2 DSG3s and 1 VU002 or similar frequency doubler or folder. I've got the Synth folder. There's also one available from Foxing Hour. If we had 2 DSG3s, that would give us the ability to find the absolute value of 3 channels compared to 3 sawtooths. And then each one of those would need to go through its own frequency doubler. We could also use stairs, by the way. At certain settings of stairs, we would need to really tweak it to make sure we weren't getting sort of a fractal, interesting pattern to the folding. We want a very simple, dumb, single fold here, nothing out of the ordinary. Okay, and if we supply a moving video image, we can get some pretty cool results here. And once again, I can dial in the exact look that I want using my VO5 or other pre-processing module. This is just scratching the surface here with this particular technique. I could really spend hours showing you how to build on this using multiple channels or modulating the frequency of that incoming sawtooth, applying a random voltage instead of a sawtooth, and all sorts of crazy stuff, but I will leave that as an exercise for the viewer. Very cool. All right, I hope you've enjoyed this video and learned a lot from it. I have certainly enjoyed making it. Thank you very much.